All right then. Am I audible?
Yes, sir.
Okay. So we were talking about exponential distribution, and we saw that exponential distribution can help us answer these kind of things. Now, I got just one thing in my mind, like if you want to, want to forecast when the next kind of, kind of issue like COVID we have, pandemic, if you want to predict that, you can really use exponential distribution in order to make predictions when this next kind of pandemic is going to happen. So people are doing it, and they are, they are truly making difference to our lives by using these techniques in order to make forecasts, right? And not everyone can do it, and not everyone should do it. It really needs a domain expertise. Like I was telling you before, you should belong to that domain. That's very important, so that you know every dynamics related to that domain. Okay, now let's move to one of the most talked about. That's why I kept it at the end. And one of the most talked about and one of the most important distributions of the whole statistics. That's called normal distribution. Everywhere you see a normal distribution, and everywhere you hear about normal distribution, and you every day see distribution, these kind of curves on your news channels, on newspapers, on your research papers, on I think everywhere you find this kind of distribution. Now, the normal distribution is also known as Gaussian distribution, right? In literature, you may find this Gaussian distribution associated with normal distribution, or some people call it bell-shaped distribution because of the shape which it exhibits. So what is this normal distribution? And it really is normal. And some people discuss, more about why it is normal. Why it's called normal distribution, rather, is that it is related to nature. It comes up from everywhere, and most of the natural processes exhibit this kind of distribution, right? So a natural process generates outcomes. Let's recap why we are here. A natural process generates, or any process generates outcomes, and most of the natural processes, their outcomes, let's say it generates X outcomes, and those X outcomes have a probability distribution, and they exhibit a normal kind of probability distribution, right? Why is normal distribution so important? Most of the natural processes generate outcomes in normal fashion, where what is a normal fashion is that the data tends to converge towards the mean, towards the center, right? So the majority of data you will see around the mean. You remember in previous sessions, we talked about empirical rule and what we call 68, 95, 99 rule. And actually that rule is applied on normal distributions, right? And they very well work, with the normal distributions. And we use that empirical rule in order to make assessments, in order to make calculations. And the other reason for normal distribution to be very popular, first, it comes from the natural processes. Please remember why normal distribution is process is famous. All natural processes generate data in normal fashion, and this normal distribution follows empirical rule, right? Another thing is that normal distribution, another advantage that normal distributions follow a strong mathematical consistency and observance. And we'll see what that means. When you cannot, now this is very important and this is very tricky. When you cannot figure out the distribution, you got a process data in front of you, or you got a process in front of you, and you're not sure what kind of process this is. Is this a Poisson process? Is it a Bernoulli process? Or is it some other process? You're not sure about the kind of process at your hand, and you're not sure about what kind of data I have in front of you. Now, the refuge, I should say the refuge distribution, the distribution where you should go is normal distribution, right? Why normal distribution? If you don't know which distribution the data is, the only distribution which can take you under its own umbrella is normal distribution, right? Why? Because it's natural. One thing, natural. So most of the processes at your hand are natural processes, right? They exhibit, even some mechanical processes also exhibit natural or normal distribution. And second thing, this distribution is symmetric. What does symmetric mean? Symmetric means that the, for example, if this is the distribution, if this is the normal distribution, and this is the mean of this distribution, 50% data lies on the lower side of the mean, and 50% of data lies on the highest side.
Excuse me, sir.
Sorry. Yes.
Sir, the slide is not visible.
Wait. Okay. Let me check. Is it visible now?
Yes, sir. Yes, sir.
Sorry for that. So this is normal distribution. Let me repeat it again. Some of you missed it. So this is also called as Gaussian distribution, right? And some people call it bell-shaped distribution, right? This is the most talked about distribution in statistics or in any science, right? Why is it popular? Because all processes, all natural, all of them, most of, I should not say all, most of the natural processes follow normal fashion or normal distribution, where the data tends towards the mean. That majority of data is just in the locality of the mean, right? Some of you who have a computer science background know a concept that's called locality of reference. I don't know if other people know it or not. So this kind of distribution follows a locality of reference rule, right? Anyways, another or another, or I should say, the most prominent advantage of this normal distribution is that it follows an empirical rule, like the 68, 95, 99, and we will see again what it rule means. And then the normal distributions have a consistency in mathematical and other observances. Now, when you cannot figure out a distribution, you always go for a normal distribution, right? I told you that if you don't know what kind of distribution you have at your hand, you always go and map your data with the normal distribution. Why? Because it's natural, it's symmetric. I was telling you why it is symmetric is that, for example, if this is your distribution and this is your data, and you found the mean of this data, let's say the mean of this data was X. Now 50% of data will be less than X and 50% of data will be more than X, and this is not true in other distributions as well, right? Because this is symmetric. And now you may say, what is a non-symmetric distribution? Let me draw it here. Non-symmetric distribution is, for example, you may have a long tail on one side and you have like this, like this, right? So you can see a long tail. So the mean, for example, you got a mean here, right? So you can see this is not a symmetric kind of distribution. So this is right left tail distribution, what we call skewed distribution. Another thing with normal distribution is that it's a unimodal. Unimodal means there is a single one top. So the mode is here. You know what's the mode of a data? Mode is the highest value, right? So the mode is here. So this kind of distribution has a single mode. Now let me make it clear. This is a single mode distribution. You can just have one single top. This is the mode. We call it single model. Now you may say, what are the other non-single model? Sometimes we have a bimodal. This is a bimodal. And you have two spikes. Right? Sometimes we may have a trimodal. We may have three spikes, but in uniform distribution, we generally have a single mode, right? Single spike or single top. Now this is a bimodal kind of distribution, right? And the third thing, which is which is very common to some of other distributions as well, is that the mean, the median, and the mode are same in a normal distribution. This is very important for those who want to perform some mathematical things with this mean, mode, median, and mode. They all are equal in a normal distribution. And the another advantage is, why we go for a normal distribution in cases where we are not sure about so many things, is that the normal distribution follows central limit theorem. Now, what is the central limit theorem? Let me give you a glimpse of it. In future sessions, we are going to take it. Is that when the size of your sample increases, right? When the size of your sample increases, your sample starts behaving like your population. That's quite natural, or that's quite common sense. So that is central limit theorem. If the size of your sample increases, the sample starts behaving like your population. Okay. So normal distribution also follows this kind of concept as well. Anyways, now what are some household examples of this normal distribution? Birth weight of babies. It follows a normal distribution, right? And height of humans, it has a normal distribution. Shoe sizes, it has a normal distribution. Test scores you get in test scores, it's a normal distribution, because you will always see, for example, this is the curve of the test scores you got. Now this is the mean, right? Let me describe the X bar. Now this mean, you can see majority of the students perform here in this area, right? Majority of the students who perform in this area, right? So we can have some extreme values. Please make sure that you don't understand this as the highest value. No, 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 not here. It's the highest probability, right? And you will see that some of the people with highest values, larger than the mean, right? Some of, let's say, these are the students which perform, A plus, right? This is the A plus grade, the highest grade you get, right, in a score. And this is the D kind of grade, or D minus, I should say. This is the lowest kind of grade. So see, this is lower than the average, but majority of students get an average score, right? They get a score of 60-70%, and some of them, only few of them perform excellent, and few of them get fail or get a lowest, but most of them perform in the mid range. That's why we call that test score always follows the normal distribution. Now, one more caution I want to give you here is that not all normal distributions are same, right? Or they follow 100% empirical rule, but they tend to follow the empirical rule to a larger extent, and you can rely on an empirical rule that standard deviations, right? Then another example of normal distributions which we see is in blood pressure of humans. If you see blood pressure of humans, you have a if you draw it curve, you have a curve, and most of the humans have just the mean blood pressure of every human. Now, everyone has a blood pressure around this value, and so we have people, most of the people fall within this range, but some have extreme. Some have high blood pressure. Only few have high blood pressure or low. Okay. Now these are some examples of normal distributions, household examples, but you can relate your own problems with normal distributions. Okay. Now, how does a normal curve behave, or how does a normal curve exhibit itself? Is that normal distributions have different shapes, right? They have different shapes depending on the mean and the standard deviation. What does it mean? It means that, for example, this is a normal distribution. This is again a normal distribution, and let me draw one more normal distribution, and can you change it in color, right? Now this is again, okay, this is a normal distribution. Now this again is a normal distribution. This is again a normal distribution, right? Now if I change another color, now This again is a normal distribution, right? Now, what's the difference between these normal distributions is that, for example, they all follow the same mean value. They all follow the same. Well, I'm assuming that they all follow the same mean values. Now they have a different spread. Different spread means different standard deviation, right? So a normal distribution may have same mean and different standard deviation, or they may have different standard deviation and different means, right? For example, this is a normal, was the mean of a normal distribution, right? And another normal distribution which we draw here is like this. So the mean is here for this normal distribution, right? So here its mean is here, its mean is here, kind of thing. So we can have different curves or different shapes of normal distribution depending on the mean of that normal distribution, mean of that data, and the standard deviation. Okay, now this is a curve. This is an ideal curve of a normal distribution at your hand. Now these are the number of occurrences, right? This is a frequency curve, and this is the number of outcomes. So these are all outcomes, right? Outcome 0 has this probability 1. Then empirical rule, let's recall what empirical rule was about. It was about the 68% of the data falls within one standard deviation of the mean, right? That's applicable in normal distribution, and 95% of the data falls within two standard deviations, and 99. So we can say almost everything falls within the three standard deviations away from the mean, right? Now, what does it mean here? What can we infer from this is that if you have a low standard deviation, this is a normal distribution, and we have another normal distribution that's like this. Okay, now we can see here the standard deviation is more because the spread is more and the standard deviation is less, right? So here you can see that the data is more close to the mean, right? And people who have problems like missing values or other things, they should know that if the standard deviation is very low, you can replace a missing value in your data with the mean. The standard deviation is very low, but if the standard deviation is high, the variation is high, you should use or restore to other ways of solving that problem of missing value, right? So this is the empirical rule which we have. Now, one more concept before we conclude today is normal versus standard normal distribution. Most of the time we use normal distribution, but in practice or in practical usage, we go for standard normal. It's just a variation of the normal distribution. Now, each value in a normal distribution is sometimes called as a raw score. We call it raw, right? It's not processed here. So whatever values you have in front of you, that's called a raw score. And we transform each value into a Z score. What's a Z score? You know, that day we perform in the previous session, we perform, standardize the data, right? Normalize the data, bring the data in standard coordinates, and you want to bring each value into the standard coordinates. And that distribution is called Z score, right? And the distribution, we call it standard normal distribution. So standard normal distribution is nothing. For example, you have values here. For example, you have values here. This was a value of something. Let's say it represents the height, and you have some values here, right? You have some values here. Now, what you do, you do one thing. You bring these values in a standard form. Let me call it X dash, right? So you convert these values into a standard form, and then this distribution of this standard values or Z score value is called standard normal distribution. Now, how these are different? Now, this is how a standard normal distribution looks like. I told you that day that the standard normal distribution has the data in the standard coordinates or normalized coordinates has always the mean of 0, right? And standard deviation of 1, right? So you can see the standard deviation of 1 and the mean of 0 in a standard normal distribution. Now, how does this help us is that once you have data from different multiple sources, and what you are going to do is you want to compare that data, right? Now, when the mean is same, when the mean is 0 rather, you can compare the data, with respect to, and when the standard deviation is also same, you can compare the data from different sources, right? So that's called standard normal form. A normal form or a normal distribution where the mean is 0 and the standard deviation is 1. Now this is a comparison between the two curves. Now this is same, even standard normal form, you should remember standard normal form also follows empirical rule as it forms as normal distribution follows, but that's the difference is here. You have mean here, you have some value for the mean, and you don't know, it may be some value, some continuous or a non-continuous value, for example, for the mean. But in the standard normal form, you always know that your mean is 0, right? And then you have a standard deviation form. And here you have some standard deviation, but it's not necessary you have standard deviation. So this is how you have a difference between normal distribution and standard normal distribution. And one more important thing to note is that you always transform data to the standard normal form, and you always use standard normal distribution. So this is one last thing for today. Most of the real world, I should write world. Most of the real world data either follows the normal distribution or you are compelled to believe so. Why you are compelled to believe that your data follows the normal distribution? Because of so many reasons I told you, right? It's easy to comprehend, it's easy to deploy, it is easy to manage it, right? That's why you are compelled sometimes to believe that your data follows the normal distribution. Thank you so much for being us today. If we have some questions, we can take them on, and let's stop the recordings first.